So in this session, I will discuss a homogeneous first order ordinary differential equation. Now, we shall consider a differential equation that will take the form dy by dx is equals to f of xy divided by g of xy. And we have a differential equation. This differential equation must satisfy a special condition that the functions f and g are both homogeneous of the same degree. So what do I mean by saying that a function is homogeneous? First, before I say what I mean by the function is homogeneous, I want to define the term degree in reference to a function of two variables. If we have a function, say for example, a function of two variables x and y, defined by, say, x squared y cubed plus 3 y raised to the power of 5, for example. Now we say we define the degree of a given term as the sum of powers of x and y in that term. So for example, if we consider the first term here, which is x squared times y raised to the power of 3, then if we want to know the degree of this term, we are going to add the powers of x and y in this term. So in this case, we see that the power of x is 2, the power of y is 3, so we add, and we see that we get a value of 5. In this case, we are going to say that the degree of this term is 5. If we go to the next term, which is 3xy raised to the power of 5, we see that here x is raised to the power of 1 in this term, x is raised to the power of 1, y is raised to the power of 5, and so if we add, we get 6. So in this case, the degree of this term is 6. Now, we say that a function is homogeneous if all the terms of that function, if all the terms occurring in that function are of the same degree. So a function like f of xy considered here, where the first term is of degree 5 and the second term is of degree 6, is not homogeneous. This function is not homogeneous because the terms are not of the same degree. But if we write a second function and write, say, f of xy, which is equals to, say, x cubed y plus x squared y squared plus 4 or 5 y raised to the power of 4, and we try to check the degree of each term. The first term is x cubed y raised to the power of 1. If we look at the degree for this term, we have the power of x is 3, the power of y is 1, so this will add up to 4. So that term is of degree 4. If we go to the second term, which is x squared y raised to the power of 2, and we check the degree for this term, the power of x is 2, the power of y is 2, and therefore when we add, we get 4. Therefore that term is also of degree 4. If we go to the third term, the term is 5 y raised to the power of 4. There is no x here, meaning that the power of x is 0 and the power of y is 4. When we add, we get 4. And so we say that all the three terms are of the same degree 4. All the three terms in this function are of the same degree, which is 4. So such a function, we shall say, is homogeneous of degree 4. We say that such a function is homogeneous of degree 4. So now we want to consider a special class of differential equation. We want to consider a special class of differential equations which can be expressed in the form dy by dx is equals to f of xy divided by g of xy, where the function f is homogeneous, the function g is also homogeneous, and the degree of the two functions is the same. So that if the function f is of degree 2, the function g must also be homogeneous of degree 2. That is, if the function f of xy is homogeneous of degree 2, then the function g of xy must also be homogeneous of the same degree 2. So in such a case, the differential equation will be said to be homogeneous of degree 2. Say, for example, you have a differential equation dy by dx is equals to, say, x cubed plus y cubed divided by x squared y plus x y squared. If you look at the terms in the numerator, the function f here, the function f of xy is x cubed plus y cubed. And you see that both the terms, the first term and the second term, are of the same degree y, of the same degree 3. Because in the first term, we don't have y, the power of x is 3. So this term is of degree 3. The second term, we don't have x, and the power of y is 3. So the degree of that term is 3. If you look at the function occurring in the denominator, we have x squared y plus x y squared. If you look at the first term here, the power of x is 2, the power of y is 1. If you add the powers, 2 plus 1, you get 3. If you look at the second term, the power of x is 1, the power of y is 2. And so if we add 1 plus 2, you get 3 again. So in this case, the numerator function, which is x cubed plus y cubed, is homogeneous of degree 3. And the denominator is also homogeneous of degree 3. So in this case, the differential equation is homogeneous of degree 3. The differential equation is homogeneous of degree 3. If you consider a second example, say you have dy by dx is equals to, say, xy plus x squared divided by x squared y plus y cubed. We would see that in the numerator, we have the function f of xy, which is xy plus x squared. And in the denominator, the function g of xy is equals to x squared y plus y cubed. If you look at the function f here, the first term we have x power 1 times y raised to power 1. If you add the powers for x and y, you get 2. In the second term, you have x raised to power 2, so which is of degree 2. So the function f here is homogeneous of degree 2. You notice that this one is homogeneous of degree 2. If you look at the function g, the first term is x squared times y, so the power of x is 2, the power of y is 1. If you add, you get 3. The second term is of degree 3. So this one again is homogeneous, but this one is of degree 3. So we see that in this case, the function occurring in the numerator and the denominator are both homogeneous, but they differ in the degree. They differ in the degree because the numerator is degree 2, while the denominator is degree 3. So although the function f and g are both homogeneous, but the degree is not the same. And that will mean that the differential equation is not homogeneous. So this one is not homogeneous. So although the function f and g are both homogeneous, but because the degree is not the same, then the function, or rather the differential equation, is not homogeneous in this case. So as I said, we are going to consider the case where the differential equation take this form, and both the function f and g are homogeneous of the same degree. Homogeneous of the same degree. So the degree of the numerator must be equal to the degree of the denominator. So in this case, if we let the differential equation dy dx, which is equal to f of xy divided by g of xy, be homogeneous, be a homogeneous first order differential equation, that means that the function f and g are both homogeneous of the same degree, then the transformation y is equal to v times x, where v is a function of x, will reduce the differential equation to a variable separable type. Using this transformation will reduce the differential equation to a variable separable type. Here, v is a function of x. So if you remember that, if you remember the case of the product rule of differentiation, that says that the derivative of u times v, where u and v are functions of x, if you differentiate this with respect to x, then you get v times du by dx plus v plus u times dv by dx. Now, if we consider the case where if we let u be equals to x, then we can write that so if we consider the case where u is equals to x, then on differentiating that we can get du dx is equals to 1. And then when we substitute, we are going to substitute here, u is equals to x. Then du dx is equals to 1 here. So in this case, we get, on substituting back, that the derivative with respect to x of v times x is equals to v times 1 plus u, and u is equals to x again. U is equals to x, then we have dv by dx. So basically, because we have said y is equals to v times x, where v is a function of x, then we can write that the derivative of y with respect to x is equals to v plus x dv by dx. So when we substitute y is equals to v times x, then the derivative of y with respect to x becomes v plus x dv by dx. This one can be achieved by the use of the product rule, as we have seen there. So let's do an example. You are given a differential equation. Say you are given x squared dy minus xy plus y squared dx is equals to 0. We first check whether the differential equation is homogeneous or not, because for us to apply this method, we must establish that the differential equation is homogeneous. If it is not homogeneous, then the method is not applicable. So we can see that in this differential equation, there are some terms here. X squared, this one is degree 2. Xy, x power 1, y raised to power 1. So if we add the powers, you get 2. Y squared, the power of y is 2. So this is degree 2 again. So we can see that the differential equation is homogeneous. We can rearrange this and write x squared dy is equals to xy plus y squared dx. And so if we divide both sides by x squared, we can divide here by x squared, we divide here by x squared, then we divide here by dx, we divide this side by dx. We shall get dy by dx is equals to xy plus y squared divided by x squared. And you see that in all the terms we have here, both in the numerator and the denominator, all the terms are of degree 2, meaning that the differential equation is homogeneous of degree 2. Once we establish that, we let y be equals to v times x. We let y be equals to v times x. So meaning that dy by dx will be equals to v plus x dv by dx. dy by dx will be equals to v plus x dv dx. We are now going to substitute this into the differential equation. We are going to substitute this into the differential equation. So where we have y here, we shall put v times x, and here also v times x squared. Then where we have dy dx, we shall now have v plus x dv dx. So let's substitute and see. So after substitution, the differential equation should be reduced to a variable separable type. So you see that the left-hand side will become v plus x dv by dx. For the right-hand side, the first term, you see the first term is xy. So that will be x multiplying vx, which is our y. Then the second term is y squared. So we shall have vx squared. The denominator is x squared. So if you look at the right-hand side, the first term in the numerator can be expressed as x squared times v, or the second term can be expressed as x squared times v squared. The denominator is x squared. Notice that we can factor out x squared in the numerator, so that we write x squared, then we have v plus v squared. Then the denominator is x squared, meaning that we can now divide and have x squared. When we divide, we see that x squared divided by x squared will give us 1. And so the result, we get v plus v squared. And what was the left-hand side? The left-hand side was v plus x dv dx. So that means that we have v plus x dv by dx being equals to v plus v squared. We can now transpose this. Notice that we have v on the left-hand side here, and we also have v here. So we can move v to this other side to get x dv dx on this side, which will be equals to v plus v squared minus v. So that x dv by dx becomes v squared. So this is after we subtract v here. V minus v is 0. So we are left with v squared on this side. The left-hand side we have x dv dx. So I'm going to take the reciprocal on both sides so that I have 1 over x dx by dv is equals to 1 over v squared. And then multiply both sides by dv, and the equation becomes 1 over x dx is equals to 1 over v squared dv. And you can see now the left-hand side is a function of x only. The right-hand side is a function of v only. So that the differential equation has been reduced to a variable separable type, and we have separated the variables. So from there, we can now integrate. The left-hand side, we integrate with respect to x. So we have the integral of 1 over x with respect to x. The right-hand side, we have the integral of 1 over v squared with respect to x. Notice that the right-hand side can be expressed as v to power negative 2 dv. This one is v, not x. Notice that we have v here. So we are integrating with respect to v. So we can now integrate. Integration of the left-hand side will give us the logarithm of x, and the right-hand side will give us minus v raised to power negative 1 plus a constant, or even this is minus 1 over v plus c. But remember, y was v times x, which implies that v is equals to y divided by x. So here we have v here, we can write x divided by y. Notice that 1 over v is the reciprocal of this. So where we have 1 over v, we can write x divided by y. So our solution, which was ln of x is equals to minus 1 over v plus c, we can write it as ln of x is equals to minus x divided by y plus c, where c is an arbitrary constant of integration. So basically, this is the general solution of the differential equation. Maybe I can do an example 2. Example 2, you're given a differential equation, dy by dx is equals to x squared plus 2y squared divided by xy. So we note here again, the numerator here, we have x power 2, so the degree of this term is 2. Here we have y raised to power 2, the degree is again 2. The denominator we have x power 1, y raised to power 1. So the degree will be the sum of the powers of x and y. X is raised to power 1, y raised to power 1. So when we write 1 plus 1, we get 2. So the degree of the denominator is also 2. This means that the differential equation is homogeneous of degree 2. Once we establish that the differential equation is homogeneous, then we can use the transformation y is equals to v times x, which implies that dy by dx is equals to v plus x dv dx. So we substitute these two. Where we have dy dx, we write v plus x dv dx. where we have y on this side, we write v times x. So notice that the first term on the right hand side is x squared, so that one remains. So we are going to replace y here and here with v times x, then dy dx by v plus x dv dx. So our differential equation becomes v plus x dv by dx is equals to x squared plus 2 x squared y squared divided by x squared times v. So notice that we have replaced y squared here with v times x squared, which is v squared times x squared. And in the denominator, we have replaced y with v times x and then multiply by x to get x squared times v. Now, in the numerator, we factor out x squared, so we get 1 plus 2v squared. And in the denominator, we have x squared times v. So x squared cancels out, and we get 1 plus 2v squared divided by v. And this is equals to v plus x dv by dx. So the v, the single term, the first term here on the left hand side, we move it to the right hand side, so that we leave on the left hand side x times dv by dx, which will be equals to 1 plus 2v squared divided by v minus v. This is v divided by 1, meaning that we can put these terms at a common denominator, which is v. Then we shall have 1 plus 2v squared minus v times v, which is again v squared. So this will give us 1 plus 2v squared minus v squared divided by v, which is 1 plus v squared divided by v. This is x dv by dx. So at this point, I'll now take the reciprocal on both sides. So the left hand side becomes 1 over x dx by dv, and the right hand side becomes v divided by 1 plus v squared. So if I now multiply both sides by dv, then I will have separated the variables. So I write 1 over x dx is equals to v divided by 1 plus v squared dv. So that the left hand side we have the function, the variable x, and on the right hand side we have the variable v, meaning that we can now integrate. The left hand side we have 1 over x, and we integrate what with respect to x. The right hand side we have v divided by 1 plus v squared, and we integrate with respect to v. Notice that on the right hand side rather, if you differentiate the denominator here, you'll get 2v, meaning that we can make use of the algebraic substitution. That is, you can make the substitution such as, say, let z be equals to 1 plus v squared. So dz by dv is equals to 2v. And therefore, dv becomes dz divided by 2v. So our function is the integral of v divided by 1 plus v squared dv, and therefore this becomes the integral of v divided by z, then dz divided by 2v. Notice that v will cancel out, and we get a half integral of 1 over z dz, which is a half logarithm of z plus a constant. We can write a half logarithm of az, where a is an arbitrary constant of integration. A half logarithm of az, where a is an arbitrary constant of integration, and z is 1 plus v squared. So, therefore, when we integrate here, if we go back now to our equation, when we integrate here, the left-hand side becomes logarithm of x, and the right-hand side becomes logarithm of az. So our solution will be logarithm of x, which is equals to a half logarithm of az. But what is z? Z is 1 plus v squared. Is an arbitrary constant of integration. So this is the general solution. Notice that we can write the right-hand side as logarithm of a into 1 plus v squared raised to the power of a half, using the rules of logarithms. And so we can, because the logarithm appears on both sides, then we can write x is equals to a into 1 plus v squared raised to power half, or even x is the square root of a into 1 plus v squared, where v in this case we can substitute was y divided by x. Remember, y was v times x, and therefore v is y divided by x. So we can now substitute back our v and simplify. And basically, this is how the general solution will look like. A here is an arbitrary constant of integration. So notice that the differential, for you to use this method, the differential equation has to be homogeneous. You must verify that first, that the differential equation is homogeneous. Once you establish that the differential equation is homogeneous, then use the transformation y is equals to v times x. And therefore the derivative of that is v plus x dv dx. Then you substitute this, reduces the differential equation into a variable separable type. Once you reduce the differential equation into a variable separable type, then you separate the variables and integrate. You separate the variables, then integrate. The left-hand side should be an integral with respect to x. The right-hand side should be an integral with respect to v. Then, make sure you apply the correct methods of integration at this point. So that is key, that you apply the correct methods of integration. Then finally, after you integrate, replace now v with y divided by x, and you have your general solution. So basically, that's the method for solving the homogeneous first order ordinary differential equations.